So we're going to talk about VSEPR theory. So what is, and molecular shapes in general, and so what is VSEPR theory? That's going to be what we're going to summarize, and then how that applies to molecular structures, and then we're going to predict the shapes of and bond angles of a molecule. And we'll maybe touch base on hybridization, but I won't go into too much detail. We're going to talk about atomic orbitals briefly when I talk about hybridization. Okay. So the VSEPR model is used to determine molecular shape. So we're going to talk about what that is. You did a lab on this with balloons. I believe you were in class for that, but you probably didn't get to really get through the information well and feel confident in it. So I won't go over this anymore. So the shape of a molecule is going to be determined by physical and chemical properties. Okay. So the molecular geometry, we can determine this with what's called the valence shell electron pair repulsion model, or VSEPR model, and it's talking about how electrons want to avoid each other as much as possible. So you're always going to have electrons that are in bonds and electrons that are on their own as far away from each other as potentially possible. Okay, so the more bonds you have, the more likely you are to have different shapes, because you're going to have electrons moving away from each other. So they're going to repel each other and cause molecules to end up getting stuck in positions. Okay. If they're an unshared electron pair, they're also going to play a role, but they're going to change it a little bit differently than an actual bonding pair. So, like I said, they're going to be as far apart as they can be from each other. So here's some examples. So in beryllium chloride, right, you actually have a linear model, molecular shape that is linear. So you have beryllium in the center, and then you have chlorine on both sides. So there's two total pairs in the bond, and two that are shared pairs. Okay, so they're both being shared. So there's no electrons here, there's no electrons here. So essentially this becomes a linear molecule, because these electrons want to be as far away as possible from each other, and guess what? That means that the maximum separation is 180 degrees. Oops, sorry. In aluminum chloride, which, just to give you a little hints here, okay, both beryllium chloride and aluminum chloride essentially should be ionic compounds, so we shouldn't be talking about molecular shapes this way, but they still are going to form molecular shapes even though it's ionic bonding and not covalent bonding. I like it better when the examples are ionic, because it's better, or sorry, covalent, because it's better when we're talking about covalent bonding, but sometimes it applies with ionic compounds. So aluminum chloride, right, you got aluminum in the center, it's got 3 bonds between the chlorines, and so they're all going to be as far away as possible. Well, 360 is all the way around. Each of those bonds between each other, you're going to have 120 degrees. Okay. With CH4, right, methane gas, okay, you get carbon in the center, and each of these are going to be angled 109.5 degrees from each other, and there's no valence, there's no lone pairs, right? So if you notice all 3 of these on this page, no lone pairs, because the lone pairs would influence the shape of the molecule. In this case, though, the carbon here, right, all of its electrons are being shared in all directions. What is hard to tell is that this one right here is actually going out and behind, so it's almost like this is 3D, right? So you can probably see this better right here. Trying to think how I can show you this with my hand, but essentially if this is the central atom, right, you got one that's coming in, one that's going out, one that's going out the other direction, and then there's also one pointing up on the top, okay? So they're all going in different directions. There's 2 more shapes I want you to know, the trigonal planar and bent, and if you notice with both of these, you have the lone pairs that are represented by this big giant shape. And basically why they have that big giant shape is to show you that this is the region that electron, or that lone pair could be found. So this is like the area in which it could be found. So because it's lone pair, they have more room to move around because they're not stuck in a bond, and because of that, it forces downwards these that are paired up in a bond downwards, right? And so even though water has two single covalent bonds, right, just like in this last diagram, beryllium chloride has two single covalent bonds, it doesn't matter. They're not going to have, it's not going to be linear because you have those lone pairs of electrons around oxygen, okay? In trigonal planar, you're going to have a lone pair, and then you're going to have three single bonds, okay? So one thing to note, okay, and that we talked about in the lab, but basically with these molecules here is they have no lone pairs, and so they're all going to be what we call non-polar. Essentially, at least generally speaking, you're going to have no polarity, basically meaning that both sides of your molecule or all the sides of your molecule, they're equally being pulled on in one way or another, where in a polar molecule, something's not equal, and so essentially there's going to be pulling that's going to force a molecule to move in one direction or to have more of the electrons in one space. But generally speaking, these three are going to all be non-polar, or these two are going to be polar because you have these electrons here that are not bonded, so nothing's pulling those electrons anywhere, right? So either this atom here is stronger and pulls those electrons from these bonds towards itself, or the electrons on the outside are the atoms on the outside are stronger and pull the electrons away from the central atom, which means that then that molecule moves away from the central atom, and that makes it polar, okay? So real quickly, just to go over that, we can actually use electronegativity values to determine bond type. So we're going to look at polar and nonpolar, because I think it's important to continue with that from the last section. And we're going to talk about the characteristics of covalently bonded compounds overall. So if you remember, electronegativity from periodic trends is a trend of the periodic table where the electrons are going to, the atoms are going to have the ability to take electrons from something, okay? So it's taking, it's the electronegativity. If something's very electronegative, it is good at taking electrons from other atoms. So the nonmetals are really good at this, and especially the further to the right of your periodic table, the further down a period you go, you're going to have higher electronegativity. We'll look at what a polar covalent bond is and define it. The main idea is that chemical bonds' character is related to each atom's attraction for electrons. So, unequal sharing of electrons results in a polar covalent bond. Equal sharing of electrons results in a nonpolar covalent bond. Bonding's often not clearly ionic or covalent as much as metal-nonmetal is going to be ionic, and non-metal-nonmetal is covalent. There's a lot of middle space, and that's where we look at polarity, okay? So, based on these negativity values, electronegativity values, right, these guys over here stink at holding on to their electrons. These guys over here are really good at taking electrons, hence ionic compounds form between metals and nonmetals. When it comes to nonmetals bonded with nonmetals, sometimes they share pretty well. Other times you get fluorine bonded to, say, hydrogen. Fluorine's going to be pulling that hydrogen away from, pulling the electrons away from the hydrogen, okay? Noble gases aren't even on here, and that's because they're not forming compounds, so they don't have a desire to take electrons. Okay, so this table is going to list the character and type of chemical bonds that form when different electronegativity value differences are found between a bond. Okay, so we're not looking at the overall molecule. It's not like, okay, I got CH4, so what's the difference between carbon's electronegativity and all the hydrogens added up or something? It's a carbon and a hydrogen. What's the electronegativity difference? Okay, so if I go back to two screens, oops, sorry, I went the wrong way. Carbon's got 2.55, hydrogen's got 2.20. So the electronegativity between carbon and hydrogen, the difference is 0.35. Okay, so difference just means it's like an integer, right? It's positive or negative, it ends up being positive. So 0.35 on this would mean that it's actually mostly covalent, right? So it's pretty evenly being pulled between both of them. A polar covalent bond is forming when the atom pulls on electrons in a molecule unequally. And then we look at the difference, and if there is a greater difference where one pulls it more than the other, then we call it a dipole because it has two poles to it, right? Dipole, two poles. So in HCl, the chlorine pulls the electrons more towards itself than the hydrogen, so much more that it's almost like the electrons spend the majority of their time around the chlorine and the hydrogen's kind of left over here on its lonesome. We can draw these sigma bonds, okay, with a plus or minus to represent kind of their relative charge. It's not a full charge, it's a partial charge. So if we were to look in a magnetic field, okay, polar covalent bonds are going to align, right? So if I put it into a magnetic field and it was a polar covalent bond, it's going to move itself into a direction that orients to the charges of the field. But if it's nonpolar, it's almost like it's kind of like the difference between if I have something that's metal, right, and if I put a magnet to it, it's going to pull on it, right, versus if I stick it to, say, something that's paper or plastic, which mostly is made of nonpolar bonds, nothing's going to happen, right? Polar covalent bonds also will dissolve in water, and other polar or ionic substances will also dissolve in water. Nonpolar are only going to dissolve in nonpolar chemicals such as milk, hot sauce, soap, things like that, right? So if you have nonpolar chemicals, so a good example of this is lipids, right? Lipids are nonpolar. They're only going to dissolve in other nonpolar substances. This is great right now with the coronavirus, right? The virus's outer layer is made of lipids, and so you actually use soap to break down those lipids because lipid, it's like, and so it actually pulls on them and it pulls them apart. So you can actually break down the virus's outer membrane with soap. And then also when you wash your hands fully and rinse it, the water is also going to help with moving the inside material of the virus off your hands. So both those actually help in getting rid of the virus. So that's why I keep washing your hands right now. Okay. With covalent compounds, right, if it's two oppositely charged ends between two polar molecules, we call it a dipole-dipole force, right? So when those two are attracting each other and pulling on each other, right? So if I got a water molecule and another water molecule, they're actually going to attract to each other and pull each other through hydrogen bonds, okay? You see this with fluorine, oxygen, and nitrogen when they're bonded to hydrogens. Hydrogen bonds are not true bonds. They are a pseudo bond. Okay? And they can create surface tension. So essentially because of all those hydrogen bonds in water, when you hit the water in a belly flop, right, it hurts a lot because those hydrogen bonds, they're not real bonds, but they want to stay together as much as they can. So when you try to break it with a force that's covering a lot of them, they don't want to break, and so there's tension. But that's why divers go in with just their feet, because their feet can break a little bit of the hydrogen bonds pretty easily, and then it loosens a lot of them. But if you just go in on your whole belly, it's going to hurt a lot. Okay. So real quickly, let's look at water and CCl4, or carbon tetrachloride. Both these bonds are polar, but water is polar as a molecule. Okay, so water is hydrogen and oxygen, right? Those individual bonds are polar. So are carbon and Cl. Carbon and Cl would be polar also, but because of the shape of the molecule, right? Water's molecule is that bent shape. It's going to be polar because those two hydrogens are actually going to be pulled upwards by the oxygen. With CCl4, the chlorines are all going to be pulling the carbon in the same equally in each direction, and so it's actually overall going to be nonpolar. Okay, I'm not going to go through the rest of this, but these questions right here might be really helpful for you to answer.